Hello, everyone, and welcome to the next lecture of the course Reasoning LLMs from Scratch. In the last lecture, we looked at policy gradient methods. Let us do a quick recap of policy gradient methods and move ahead to the chapter which we are going to cover today, which is called as Generalized Advantage Estimation. So, in policy gradient methods, we looked at two steps. Step number one was parameterizing the policy. This meant that from the notation pi of st comma or pi of s given a, which is the probability of, should be reverse, pi of a given s, probability of taking action a while being in state s. This was converted to pi theta of a given s, which means that we have a policy parameter which is used to parameterize our policy. So we are going to express our policy in terms of this policy parameter which is called as theta. We also looked at one simple way of expressing this with which is soft max in preferences. Now once we have parameterized our policy, our main objective behind any reinforcement learning problem is to make sure that we are getting maximum rewards. The agent gets maximum rewards in the long run. So we have to define a performance measure which we want to maximize. Now the performance measure is denoted by j of theta, and we said that the performance measure can simply be the value function, the value function for the initial state of the episode, which is v pi theta s of 0. This essentially means that let us look at the initial state when the agent begins and let us sum up all the rewards which the agent is receiving in the future, calculate the expected value of all these summed up rewards, and say that we are going to maximize this expected value, and I am going to find the policy parameter which maximizes this. Now once we define this, the natural challenge which lies ahead is, let's say this is the curve which we have for j of theta, where on the y-axis you have j of theta and on the x-axis you have theta. So your aim is to basically climb up this steep mountain and reach the maximum of this curve. And to climb this mountain, at every point, I need to know what is the slope. What is the slope at each and every point? And this is, in fact, the gradient ascent method, which we will use to find the policy parameter which maximizes this performance measure. Now the question is that how do we find the slope? How do we find the gradient of this performance measure with respect to the policy parameter? And this gradient is denoted by, so I'm going to go down a little bit and write it over here. This is denoted by grad of j of theta, which is the gradient of the performance measure with respect to the policy parameter. Uh, now, we said that this performance measure is going to be a combination of two things. The first thing is, uh, let's try to think about what will happen if I change this policy parameter. If I change this policy parameter, the decision which my agent takes for every state will change, which means that if I go to any state S, the action which I am taking at that state will change. Now, a consequence of this is that the state distribution of the agent is going to change. So, this is the state distribution. Let's say these are the states, and on the y axis, I'm counting how frequently are these states visited by the agent. That is affected by the policy, and the second is the gradient, or let's replace the gradient by the change in the policy itself. So this we denote by grad pi of theta. So now the challenge that we faced while calculating this gradient was that the gradient involves two independent gradients. The first is the gradient of the state distribution, and the second is the gradient of the policy itself. And then this is a tough problem to solve because it's hard to find how will the state distribution change as the policy parameter changes. But then we saw that there is a very nice theorem which is called as the policy gradient theorem, which told us that don't worry about the state distribution and how it changes, only worry about the change in the policy. So only worry about the change in the policy. And this made the calculations easy. And we looked at uh, how the gradient of the performance measure is proportional to. Uh, so essentially, what we saw was the gradient of j of theta is proportional to the state distribution mu s, and then we sum over all the actions and we do q pi of s comma a, and then we do grad pi a given s theta. So essentially it only depends on the gradient of the policy. It does not include the gradient of the state distribution itself, and this was a very powerful result for us. And now with these five steps, we have a complete picture. We can now write down the gradient ascent rule as follows: theta t plus 1 equal to theta t plus alpha, which is the learning rate, times grad of j of theta. And within this grad of j of theta, you can now substitute this expression. So this is how the policy gradient methods work. And then we looked at, okay, fine, we substitute this expression, and then we did some manipulations with the expectation sign, and finally we saw that the expression for the gradient of the performance measure, which can be directly used as an input in in the policy parameter update rule, is given by this expression, which is the expected value over the policy of multiplication of two parameters. The first is what are the expected rewards you are going to get after choosing action 80 while being in state ST. This is the first term. And the second term is given by grad pi divided by pi. Now, this term is something which we are going to encounter a lot. So I want you to get familiar with how the numerator looks and how the denominator looks as well. The intuition behind this whole expression is that, let's say, and please understand this carefully. Okay, so let me try to visualize a 3D diagram where on the x axis you have theta 1 and on the y axis you have theta 2. These are the parameters of our policy. And imagine that this is a 3D curve which is projecting out of the surface. And what this curve is depicting is this curve is giving us pi of at given st, which is the probability of choosing action at while being in state st. Now, what this expression is telling us is, let's say, okay, so let's say I am somewhere here, right? Uh, this term, grad pi divided by pi, is the direction of the gradient along this curve. So, case 1 is if q pi is greater than 0, q pi of st comma at is greater than 0, this expression tells us that we are going to move in the upwards direction. And if q pi of st comma at is less than 0, then this expression tells us that we are going to move in the downward direction like this. And this makes a lot of sense because if q pi is greater than 0, it means that whatever action I am taking, it's leading to positive rewards in the long run. And I should gradually move in the direction which maximizes the probability of choosing that action when I am in the state st. But if q pi is less than 0, it means the action is not very good and I will penalize the action. I will say that if q pi is less than 0, don't move in the direction of maximizing the probability, but move in the opposite direction, which minimizes the probability. I want all of you to close your eyes and imagine why this makes sense. Imagine a curve projecting out of a 2D surface and moving towards the top of the cliff of the mountain if the expected rewards are positive, and then moving towards the bottom of the mountain if the expected rewards are negative. This is exactly what this expression tells us and why it's so intuitive and it makes a lot of sense. Now, once we have understood the intuition behind the expression of the gradient of performance measure, the above expression can also be written as like this: gradient of log pi. And the reason is that gradient of log of f of x can be written as 1 by f of x into gradient of f of x. So, in a lot of textbooks, papers, if you don't see this, but you see this expression, then don't get confused. Both are one and the same. Okay, now we are going to look at some other ways in which we can write this same expression. Firstly, we have looked at q pi of st comma at multiplied by gradient of log pi. Now there are some alternative ways in which this same expression can be written. Remember that q pi is the expected value of all the returns after taking action at in the state st. So it can be written as expected value of pi of gt, where gt is the expected return. Remember in the Monte Carlo, or GT is the actual return, it's not the expected return. And if you calculate all these actual returns and take an expectation over them, what you get is Q pi for a fixed action, of course. Now you substitute this back into the original expression and you get this expected value of pi of expected value of pi gt given st comma at. Now it turns out that this expression can simply be written as expected value of pi times gt. uh, there is a theorem in probability which allows you to do this, but I don't expect you to fully grasp it at the moment. So just assume that this can be written like this, and we can write this expression as expected value of pi gt times grad of log pi s uh, at given st. So here, wherever I have written st comma at in the pi, uh, make sure that in your mind you replace it by at given st. It's a typo which has happened in the notes at the moment. I will correct it. Okay, so now what we have seen is there are two ways of writing the gradient of the performance measure. One thing is one method is to simply have q pi as the first term, and the second method is to have q pi replaced by gt. The difference with both the methods is that in the first method you will need to take an average of all the actions, and you will need to find the expected value of all the returns. And then in the second case, you don't need to average out all the returns after taking action 80 from state st, but you can just take one single return from st and 80. So in a practical scenario, the second expression is much more useful, as we saw in the Monte Carlo methods as well. Remember, in Monte Carlo methods also we use gt, so that's why it is more practical. Now, okay, so there are two ways of writing grad j of theta, which is the gradient of the performance measure. The first is simply have q pi over here, and the second is replace q pi by gt. The second method is called as reinforce method. Now we looked at there is a third method of evaluating the gradient where what you do is you simply subtract a baseline from the actual return. So this is the return, and this is done because usually the reinforce method it induces a lot of variance in the data, because you are sampling from multiple states, and uh, these samples can be completely different. So if you reduce or if you subtract each samples from a baseline which depends only on the states and not on the actions, it turns out that you can reduce the variance to a great extent. So in practice, there is always a baseline which is subtracted from the Monte Carlo return, and then the actual expression looks like this. So there are three methods: method one, method two, and method three, for solving these problems using the policy gradient methods. Now, in this lecture, we will look at one more method which is used for expressing the gradient, and we will replace this term with something else altogether. And why we do that is because it offers a computational advantage to use that term instead of these three terms which we looked at, and it is the most common implementations in all the modern algorithms like ppo, which is used in reinforcement learning with human feedback. So that is why this lecture is very important, because it helps us to build a very nice framework to understand these important algorithms in the context of uh, reinforcement learning, modern reinforcement learning, and especially their applications to large language models. Okay, so this brings us to a concept which is called as advantage function. So, an advantage function is a quantity which measures whether an action is worse or not compared to the policy's default behavior. Now, what does this exactly mean? Let's say you have a state st, and then from this state st, you have a lot of options for taking the actions. You have a1, a2, a3, A4, A5, etc. But the way, so you are following the current policy at the moment, and let's say in that policy you are choosing the action A2, and when you choose the action A2, you are getting an expected reward of, so let's say you add up all the rewards you get in the future after choosing action E2, you are getting an expected reward of 50. So this is the default value of the policy. But what if I choose action A1 and I get a cumulative expected reward of 80? This means that action A1 is better than action A2 for that particular state, and your policy's default behavior can be optimized more because there is scope for optimization. So this difference is what we called as is what we call as advantage. So the advantage of ST comma A1, let's say, is 80 minus 50, that is 30. So if the advantage is positive, it means that whatever action you are looking at, it is better than the policy's default behavior. But now let's say A5 has a cumulative expected reward of 20. So the advantage of ST comma A5 would be minus 30, which is negative and means that the action should not be favored compared to the policy's default action. Now, what are we doing here when we are subtracting 50 minus 20? Can you pause and think about it? We already know the definitions for all of this. So, this 50, which is the policy's default behavior, is nothing but the value function of the policy, and 80 is the action value function, which is q pi of st comma 80. So the advantage function is actually defined by the difference between the action value function and the state value function, which is q pi of st comma 80 minus v pi of st. So let us say we encounter a state and action pair for which the advantage is positive, which means that q pi of st comma 80 is greater than v pi of st. This implies that our policy is choosing some action which is performing worse in the long run compared to the action 80, and there is a scope for improvement. And we had this same intuition in the policy iteration step of dynamic programming, if you remember. What we did in dynamic programming is that we fixed one policy, we calculated the value function for that policy. Then what we did was we went to a state of the agent and we asked the question that is there any action in this state which is leading to a better uh, expected rewards compared to the value function at that state? If the answer was yes, then we knew that there is a scope for improving the policy. So we had the policy improvement step. If for all the states the advantages are negative, it means that your policy is indeed optimal. So, because the intuition the advantage function offers with respect to the scope for improvement of the policy compared to the default policy, we generally use it in the gradient estimation step. Now, we will do this by using two simple steps given below. So, firstly, we will use this method, which is method number one, to write the gradient, where we use the action value function as the first term, and then we use a baseline of the value function. which is method number 3, where we had a baseline. Remember, the baseline can be anything as long as it is only a function of the states of the agent and not a function of the actions. And value function is an appropriate baseline because it doesn't depend on the actions, it's only dependent on, or it's only written for a specific state. So we can easily write down the performance measure, the gradient of the performance measure, as expected value of q pi of st comma at minus v pi of st times gradient of log of policy, and this is nothing but the advantage function. So we get the following: gradient of the performance measure of the policy is the expected value over the policy of multiplication of advantage function times gradient of log of policy. And I want all of you to remember this. This is a very important formula which is referenced multiple times in all the algorithms which we are going to discuss subsequently as we move ahead. Now, the main question that we want to answer in this lecture is, how can we estimate this advantage function? Can we think about it? The advantage function we know is the difference between the action value function and the state value function. But how do we estimate this in practice? Is there an efficient way to estimate this? Can we think of some way? Let's understand it. And this is something which is called as, this method which I'm going to describe later will be called as generalized advantage estimation. I will come to why it is called like that. So we want to estimate this quantity, and this quantity can be written as, let's look at first only the action value q pi of st comma at, which is the expected value of the reward received after taking action at plus gamma times the subsequent reward plus gamma square times the reward received after that, and then you add all these rewards together. Now the expression within the brackets can be written as the immediate reward plus gamma times rt plus 1 plus gamma rt plus 2 plus dot dot dot. Now this expression within the brackets, this expected value, this is nothing but the value function for the next state. So what we can do is, we can basically write down the action value function. The expected value of this is same as the expected value of this. So essentially we have converted the action value function into a state value function. And remember, this is nothing but the temporal difference target. What this says is, you collect the next reward and then you add it to the discounted value of the next state. Where have we used this in temporal difference method? Remember, the problem with Monte Carlo methods was that to find the reward or the return, we had to add up all the subsequent rewards, which was problematic because it did not allow us to make immediate updates. But temporal difference methods really solved that problem because you only needed the immediate reward and the value function of the next state, which is exactly the expression that we are looking at right now. So basically, we can replace the advantage by this formula: RT plus gamma v pi st plus 1 minus v pi of st. The hat here indicates that this is only an estimate of the advantage function. Now remember that here we are only looking one step ahead from the state st. So it is also called as a one step backup. Now this is definitely one method of estimating the advantage function. Here we are simply using a proxy for the action value function, and the proxy is nothing but the temporal difference target. And why we use the temporal difference target is because the expected value of this temporal difference target exactly matches the expected value for the action value uh, for that particular state and for that specific action taken in that state. However, this also is slightly problematic. The reason is that it is biased. Why are we only looking at one step ahead? Why don't we look two steps ahead, or three steps ahead, or four steps ahead? And this is a natural question which can come into anyone's mind. Why are we only looking at a single step ahead? Why can't we use, let's say, a two step backup as a proxy for the action value, or a three step backup? Well, you can do that to reduce the bias. Let's consider a two step backup and see how that will look like. So, a two step backup looks something like this. You start from state st, and then you take an action, you go to state st plus 1, you take another action and you go to state st plus 2. Now, on the way, you receive two rewards, rt and rt plus 1. So you can write down an estimate for qpi as the summation of the rewards received, which is rt plus gamma rt plus 1, plus gamma square times v pi of st plus 2. Remember here that we are calculating the value function of st plus 2, whereas for a one step backup, we had calculated the value function for st plus 1. So we are looking two steps ahead over here. And after this, the advantage function now can be written as like this: rt plus gamma rt plus 1 plus gamma square v pi of st plus 2 minus v pi of st. Now this is better than the previous backup because it is using values of two rewards. So it's reducing the bias to the immediate next state. Now the question is that can we do more? Can we do an n step backup? And yes, you can do an n step backup. If n is very large, let's say you have till the end of the episode, it covers all the steps, then the QPI estimate would look like this: RT plus gamma RT plus 1 plus gamma square RT plus 2 dot dot dot. And this is nothing but the Monte Carlo return. So if you look at a division, if n is 1, then you use the TD return as the proxy for the action value function. But if n goes to infinity, n is very large, then you use the Monte Carlo return as a proxy for the action value estimate. And this is depicted very nicely in this diagram. For a one-step backup, you have a temporal difference target which is used as a proxy, but for a large step backup, for an infinite step backup, you have a Monte Carlo return, and in between you have this two-step, three-step backup. So these are the states. These hollow circles are the states. This is st plus 1, st plus 2, and st plus 3. And what you're doing is that you're simply adding up all these rewards, t plus 1, rt plus 2, and at the end you're attaching a value function to this last state. So here you will be looking at value function of st plus 3. Here you will be looking at value function of st plus 2, and here you will be looking at value function of st plus 1. So to reduce, so this is how we can do multiple step return. Now, after this, people ask another question. Okay, we can do either two step, three step, or n step return, but can we do a composite return? Can we do a return which combines, let's say, a two step return and a four step return and a six step return? That will be a very good way of reducing the bias, because here you are considering multiple steps within the same expression. So yes, you can do that. Example, let's say if we are doing a composite return where we are doing a half of one step backup plus half of two step backup, then how would the estimate for the action value look like? It's straightforward from the previous analysis. You do half of estimate for the one step backup, which is RT plus gamma times V pi ST plus 1, and half of estimate of the two step backup, which is this should be gamma and this should be gamma square, plus gamma RT plus 1 plus gamma square V pi ST plus 2. And then your advantage function estimate will look something like this: half and half, because it's a composite return, and then you subtract it from the value function. So the backup diagram would be given like this. So you have a line at the top here which indicates that we are doing a summation. So here we did not have a line because we were considering individual returns, but here you are doing summation. So you are taking half from the one step return and you are taking half from the two step return. More generally, in a complex backup, all the upcoming states are included. And there is an expression for that. Let's look at how that is done. So, what people do is that instead of assigning half and half, they consider all these states right from a one step backup, two step backup to an n step backup. And the weightage attached to each step is quite interesting. For a one step backup, they attach a weight of 1 minus lambda. For a two step backup, they attach a weight of 1 minus lambda into lambda. For a three step backup, they attach a weight of 1 minus lambda times lambda square. So, this is how the weights are given to one step returns, two step returns, three step returns, etc. And if you add all these, yeah, now the interesting bit here is that the parameter lambda allows you to control the importance or the switch between temporal difference target and Monte Carlo target. For example, if lambda is 0, then because all these terms have a lambda here, all of them will become 0, and here you will have a temporal difference target. But if lambda is equal to 1, then all of these terms will become 0 except the final return, which becomes the Monte Carlo target. So the final expression looks like this, where the advantage is given by 1 minus lambda times the one step return plus lambda into 1 minus lambda times the two step return plus dot 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 lambda raised to n 1 minus lambda times the n step return. Or here we should have n minus 1, because for one step return we only have 1 minus lambda. And this expression is very interesting because lambda allows you to control the switch between temporal difference target and Monte Carlo target. So there was a simple way for us to write estimate the advantage function. We could have simply used the one step return, but researchers have found out that if you use a composite method like this, where you have a combination of one step, two step, and n step return, you reduce the bias. You don't give importance to just one step return, but you give equal importance to all these different returns. And that's why a composite return is much more effective in practical implementations. Okay, now if lambda is 0, it means that we are only considering the temporal difference target, which is only we are looking at the next state. So bias, the bias is very high, but the variance is low because we are only considering a one step return. We are not adding a lot of different estimates together. But if lambda is equal to 1, we only have we combine the, or we add all the returns received by the agent from the start state to the end of the episode, which is the Monte Carlo return, which reduces the bias because we are adding from all the states, but it induces a high variance. And the reason it induces a high variance is because we are adding a lot of estimates together. So the variance of each estimates adds up. And another way to look at lambda is that it controls the compromise between bias and variance. This entire method is called as generalized advantage estimation, and the final expression is given by this. So, the whole objective for this lecture is to be able to write the gradient of the performance measure as the expected value of the generalized advantage estimate multiplied by gradient of log of the policy. So now we have a way to estimate this, which means that we can now successfully implement the policy gradient methods in modern algorithms. So grad of j of theta is often denoted by the symbol g, which might be used in some of our explanations in the subsequent lectures. Okay, so this brings us to the end of today's lecture. The whole point of today's lecture was to be able to estimate the gradient of the performance measure, and to be able to estimate that gradient, we needed to write the performance measures gradient in terms of advantage function. And to write that, we used a combination of uh, the action value function, and we subtracted that by the baseline. For the baseline, we use the value function for a state. And then by doing that, we could write the expression for the gradient of the performance measure in terms of the advantage. The advantage is the advantage tells us how is the action better or worse compared to the policy's baseline. If the advantage is positive, it means that there is scope for improvement. But if the advantage is negative, it means that there is no scope for improvement. So, if you consider the diagram which we had looked at before, and consider a space of theta 1 and theta 2, and let's say we had imagine this to be a 3D curve. Uh, Let me draw that again. Imagine this to be a 3D curve which denotes pi of AT given ST. And let's say I am somewhere here at the moment. Now, this gradient is calculating the tangent, and this advantage is telling me whether I should move up or down. If the advantage is positive, I want to move up because I know that there is scope for improvement, and I will move in the direction which maximizes the probability of choosing that action, since it gives a positive advantage. But if the advantage is negative, then I don't want to maximize the probability, so I go in the opposite direction. So that is how this entire formula now makes sense from an intuitive point of view. And this expression is very important for us to remember because we will be referencing it multiple times in the upcoming lectures. Thank you, everyone. And in the subsequent lectures, we will cover trust region policy optimization, followed by proximal policy optimization. Then we will have one lecture which discusses how is the agent environment interface of reinforcement learning applied to large language models. And finally, we will discuss group relative policy optimization, which is GRPO. Thank you very much, everyone. Bye.